Assalamualaikum warahmatullahi wabarakatuh. Today, we want to talk about application second order system. Our group chose Automobile Adaptive Cruise Control System as our project. Cruise Control System. Cruise Control System is a controller designed to keep the vehicle speed constant in a long run drive. ACC. ACC is an active safety system that automatically controls the acceleration and braking of a vehicle. How ACC control system works. Let's see. ACC works by monitoring other vehicles. ACC activates through a button on the steering wheel. ACC helps to control the speed limit. Alert the car. The cruise control system reduces the probability of a potential crash. It's how ACC works.
I will present the block diagram for the application and state the input, output and feedback of the application and model the system to get the system transfer function. Block diagram. The cruise control system is a second order closed loop control system. The input signal to the controller is the arrow, which is the difference between desired speed and the actual speed. According to this arrow, the controller will give the throttle control signal that adjusts the throttle angle. The opening range of the throttle change by controller will change the engine speed. The cruise controls regulate the vehicle speed based on desired speed, and the actual speed comes from the feedback magnet and coil sensor. The regulation of the vehicle speed is done by adjusting the throttle angle, while this will change the engine drive force. This is our system modeling to get the system transfer function. It's from radius and feedback. After we solve the equation, we get G1 bracket S, G2 bracket S over 1 plus G1 bracket S, G2 bracket S, H bracket S. The final value we assume is 76 over S square root plus 4S plus 100.
Hi, now I will continue our group presentation. I will present about simulation on MATLAB software and calculation. First, we have assumed for our transfer function equation is 76 over S squared plus 14S plus 100. After we assume, now I will show you how to simulate the transfer function by using MATLAB software to getting the output. Okay, now this is MATLAB software script. We need to use the input as the system input. To type hash equal to df open bracket 76 comma 1 space 14 and space 100 close bracket, enter. Next, type stapler open bracket hash close bracket, then enter. Now we get this step response graph. At the graph, right click, choose characteristic, click response, settling time, rest time, and restore steady state. Now we go to the command window. Type step info hash open bracket close bracket and enter. Then here we get the output from the graph such as rise time, settling time, overshoot, and peak time. Now I will explain about the theoretical calculation. Our second order of transfer function is 76 over s squared plus 14s plus 100. To calculate peak time, settling time, rise time, and percentage overshoot, we need to find neutral frequency and damping ratio first. First, we need to find natural frequency, which is omega n squared equal to 100. Then we got 10. Next, to find damping ratio, which the formula is 2 zeta omega n equal to 14. So the answer is 0.7. To calculate peak time, the formula for peak time is pi over omega n square root 1 minus zeta square. So we got 0.4399 seconds for peak time. Next, to calculate settling time, the formula is 4 over zeta omega n. The answer we got is 0.5715 seconds for settling time. To calculate rest time, the formula used is 2.3 over omega n. Then the answer for rest time is 0.23 seconds. Last one is percentage overshoot. The formula is exponential minus open bracket pi zeta over square root 1 minus zeta square close bracket and multiply by 100. So for percentage overshoot, we got is 4.5988%. So this is a comparison between the value from graph and also the value from calculation. As we can see, it is a little bit different from both at peak time, rise time, settling time, and also the percentage overshoot.
Convert the system's transfer function to state space representation. Okay, from the equation, we must define state variable x and then define input variable, differentiate the state variable to get the equation in metric form. Okay, this is our metric form, and then we get output equation.
To explain the stability of the system, we need to use Routh-Hurwitz table. We put the value of transfer function based on the row and column. So our denominator is s to the power of 2 plus 14s plus 100. So we take s to the power of 2, which is the biggest power of denominator. The table above show how to get the stability on the system by using Routh-Hurwitz table. Based on the calculation shows that the system is stable. The system is stable since the first column of the Routh-Hurwitz is positive. There are no sign changes based on the table above. The Routh-Hurwitz declares that the number of the roots of the polynomial are in the right half plane is equal to the number of sign changes in the first column. Next, when the system is stable, this is valid to calculate the steady-state error. We calculate the steady-state error for step input, ramp input, and parabolic input from the transfer function. The formula is ES equal to RS minus CS we assume as equation 1. Then CS equal to RS minus TS we assume as equation 2. Then we substitute equation 2 into 1, we get ES equal to RS minus TS. Then we factorize, we get RS multiply 1 minus TS. Formula of finite value theorem is ESS multiply S equal to limit S until 0 S multiply ES. And then for the TS, we use the transfer function value, which is 76 over S to the power of 2 plus 14S plus 100. For unit step input, RS equal to 1 over S. Then ESS we get 0.24. Then we calculate each step. The formula is limit S until 0 S multiply RS over 1 plus GS. Then we get 0.5682. For the E-ramp, the formula is limit S until 0 S multiply 1 over S to the power of 2 over 1 plus GS. We get infinity. For the E-parabolic, The formula is limit s until 0, s multiply 1 over s to the power of 2 over 1 plus gs. Then we get infinity also. Hence, we compare the calculation to our simulation result using MATLAB. The result from the MATLAB showing that the final value is 0.432. We analyze system simulation using MATLAB steady-state error. For the output, E multiplied by infinity equal to 1 minus 0.5682, we get 0.432. This shows that the system is type 0.
So, now I will continue about the discussion of automobile adaptive cruise control system. We know that the cruise control system is called closed loop control system. The control system which uses its feedback signal to generate output is called a closed loop control system. Closed loop system can automatically correct the error that occur in output by using a feedback loop. In automobile adaptive cruise control system, the input signal to the controller is the error, which is the difference between the desired speed and the actual speed. According to this error, the controller will be a throttle control signal that adjusts the throttle angle. The opening range of the throttle changed by the controller will be changed the engine speed. The cruise controller regulates the vehicle's speed based on the desired speed, and the actual speed comes from the feedback magnet and the coil sensor. Thus, we have seen that the response of the system in MATLAB simulation, the calculated value is almost the same for the peak time, rise time, settling time, and the percentage of overshoot. In addition, the system is stable since the first column of the root orbit is positive. There are no significant changes based on the table above. But last but not least, the graph also proves that the system is undamped and the system is in the second order system because the highest of S is 2. In our conclusion, as you can see, in a closed loop control system, feedback loop may be used to achieve system consistency, stability, and produce the control system desired output. In our case, when the adaptive cruise control is activated, the automobile will run steadily, and as a result, the unnecessary change of speed will be reduced. As a consequence, the driver enjoys more comfort and can be better concentrate on traffic. I think that's all from us, and I wish you all a good day and thank you.